Somewhere beneath the streets of New York City, threaded through the same tunnels, carrying your Netflix streams, your work emails, and your late-night group chats, physicists just proved something that should make every cryptographer, every intelligence agency, and every ordinary internet user genuinely sit up and pay attention. They took two particles of light, separated them across an entire city, and showed that measuring one instantly affects the other, not through any signal traveling through the fiber, not through any message racing at the speed of light, but through a connection so strange that Einstein himself spent decades trying to prove it couldn't be real. It's called quantum entanglement. And for the first time at true metropolitan scale, using the exact same commercial fiber optic cables already buried under a major American city, scientists have shown it actually works reliably, repeatably, and fast enough to genuinely matter for real world applications. The classical internet, the one your phone connects to right now, has no answer for what this technology can do because it isn't built on the same rules of physics at all. This is the story of how America just quietly proved a quantum internet is technically possible, why it terrifies anyone who cares about hacking and surveillance, and why the version of the internet you've used your entire life may already be sitting on borrowed time. To understand why this matters, you first need to understand what entanglement actually is, because it's one of those concepts that sounds like science fiction until you realize it's some of the most rigorously tested physics in existence, verified across nearly 100 years of increasingly precise, increasingly demanding experimentation. When two particles become entangled, typically photons, individual particles of light, their properties become linked in a way that has absolutely no equivalent anywhere in the classical world you experience every day. Measure a property of one entangled photon, say its polarization, the specific orientation its light wave vibrates in, and you instantly know the corresponding property of its partner, even if that partner sits on the opposite side of a city, or, as separate experiments have, shown on opposite sides of the planet. This isn't because the particles were secretly pre-programmed with matching values from the moment they were created, an idea physicists call local hidden variables. Physicist John Bell devised a rigorous mathematical test specifically to rule that possibility out, and decades of increasingly precise experiments closing loophole after loophole skeptics. Raised have consistently confirmed that entangled particles really are connected in a way no classical explanation can account for. Einstein famously hated this implication, dismissing it as spooky action at a distance. He never lived to see just how thoroughly the evidence would eventually side against him. Here's where the story turns from physics lecture to something genuinely consequential for how the internet itself might work in the years ahead. For decades, entanglement lived almost entirely inside university laboratories, demonstrated over short distances, using carefully controlled, vibration-isolated equipment sitting on specialized optical tables, environments about as far removed from the real world as you can get. The entire challenge, blocking any kind of practical quantum network, has always been the same, whether entanglement, this famously delicate, easily disrupted quantum state, could actually survive being pushed through the messy, chaotic, real-world infrastructure an actual city depends on, fiber optic cable already buried underground, already carrying enormous volumes of ordinary internet traffic, already subject to temperature swings, vibration from subway trains and construction, and every other kind of environmental noise a laboratory bench conveniently eliminates. If you're finding this as fascinating as I am, the actual moment quantum physics left the lab and proved it could survive a real city, go ahead and hit like and subscribe now, because the specific numbers behind how this was actually achieved are genuinely remarkable, and we're about to walk through exactly how researchers pulled it off. In February 2026, a team working in New York City finally cracked this exact problem, and the scale of what they achieved is worth sitting with for a moment. Connect, a Brooklyn-based quantum networking startup working directly with Cisco, one of the largest networking equipment companies in the world, announced the first entanglement swapping demonstration of its kind, conducted over deployed metro-scale fiber using a genuinely commercial quantum networking system. Not a specialized laboratory prototype, but hardware built for real-world deployment. The demonstration ran on what's called the Gotham Q testbed, a quantum network Connect has built running throughout New York City using existing, already installed telecom fiber. The network spanned 17.6 kilometers of deployed fiber connecting Brooklyn and Manhattan, routed directly through a commercial data center at 60 Hudson Street, one of the most important telecommunications hubs in the entire country. This wasn't some isolated point-to-point laboratory link. It was a functioning, multi-node network stretched across an actual American city, using the same physical cables already carrying the ordinary internet traffic of millions of New Yorkers every single day. The specific numbers behind this demonstration are what separate it from years of previous, more modest quantum networking milestones. The collaboration achieved swapping rates of over 1.7 million entangled photon pairs per hour under local, controlled conditions, and 5,400 pairs per hour once pushed through the actual deployed city fiber, a rate the researchers described as nearly 10,000 times better than previous benchmarks achieved using similar platforms. Just as importantly, the system maintained polarization fidelity above 99%, meaning the delicate quantum correlations between entangled photons survived their journey through the city's fiber infrastructure with remarkably little degradation, a genuinely difficult engineering achievement given how easily quantum states typically decohere or collapse into ordinary classical behavior when exposed to any kind of environmental disturbance. A separate related paper describing the underlying Gotham Q testbed reported the network maintaining over 99.5% uptime across an extended 15-day operational period, using 34 kilometers of deployed city fiber, distributing entangled photons at rates as high as 500,000 pairs per second under optimized conditions. That combination, high fidelity, meaningful throughput, and sustained reliable uptime over an extended real-world test period, is precisely the trifecta that separates a laboratory curiosity from something that starts to look like genuine deployable infrastructure. What makes this achievement even more significant is a specific technical term embedded right in the announcement: entanglement swapping. And it's worth understanding exactly what that means, because it's the specific capability that turns a simple point-to-point quantum link into something resembling an actual network. Entanglement swapping is the process that allows two photons that have never directly interacted with each other to become entangled anyway, mediated through intermediate nodes, essentially extending and relaying quantum correlations across a network the same way classical internet routers relay ordinary data packets from one part of a network to another. Researchers involved in the demonstration described entanglement swapping as a fundamental operation in the quantum internet, the specific building block needed to eventually connect quantum devices across arbitrary distances rather than being limited to direct, unbroken physical links between exactly 2 points. The orchestration software Cisco contributed to the demonstration functioned, according to the companies involved, essentially as a digital air traffic controller for the city-wide network, autonomously coordinating Quinx hardware across geographically separated nodes without requiring constant manual intervention, precisely the kind of automated, self-managing infrastructure a genuinely scalable network would eventually require. New York wasn't the only American city where this exact kind of breakthrough happened in 2026, and looking at the second major demonstration helps illustrate just how quickly this technology moved from isolated proof of concept toward genuinely repeatable, geographically distributed achievement. In July 2026, researchers at Northwestern University, working in partnership with Fermilab and supported directly by the United States Department of Energy, achieved what they described as the first real-world demonstration of quantum entanglement distributed over a genuinely busy telecommunications fiber network, one already carrying high-capacity commercial internet traffic simultaneously alongside the delicate quantum signal. A single photon carrying quantum information traveled more than 24 kilometers through an optical fiber, connection linking Northwestern's Evanston campus to downtown Chicago, arriving still entangled with its partner despite sharing the exact same physical cable as powerful, conventional data traffic the entire way. Prem Kumar, the Northwestern professor who led the research, offered a memorable description of just how difficult this specific engineering challenge actually is, comparing the delicate quantum signal traveling alongside the far more powerful classical internet traffic to an ant traveling through a path filled with elephants. The team measured entanglement fidelity above 94%, even under these genuinely challenging, noisy real-world conditions, a result Kumar described as confirming the connection survived at a level impossible for any classical communication system to reproduce, precisely because classical physics offers no equivalent phenomenon capable of maintaining that specific kind of correlation across distance. It's worth pausing here to actually explain why this specific technical challenge, quantum signals surviving alongside ordinary internet traffic on the same physical cable, matters so much for whether any of this ever becomes genuinely practical technology, rather than remaining an impressive but ultimately isolated laboratory demonstration confined to a handful of specialized research papers nobody outside the field ever reads. Building an entirely separate, dedicated fiber optic network specifically for quantum communication, one that never touches ordinary internet traffic at all, would be extraordinarily expensive, requiring cities and countries to lay brand new cable alongside the literally millions of miles of fiber optic infrastructure already buried underground supporting the internet you use today. If quantum signals can instead coexist directly alongside ordinary classical data on infrastructure that already exists, using careful engineering tricks like sending the quantum signal through a quieter, specifically chosen wavelength of the optical spectrum, and applying advanced filtering to protect it from interference, the entire cost and timeline for eventually building a genuine wide-scale quantum internet shrinks dramatically. This is precisely why Kumar and his research team specifically chose to run their experiment over a fiber cable already carrying real commercial traffic, rather than a cleaner, isolated test line, deliberately proving the harder, more practically relevant version of the underlying question. So what precisely can a quantum internet actually do that the internet you already use every day cannot? And why does that gap matter enough for researchers, governments, and major technology companies to be racing toward it with this much urgency? The single most consequential answer involves security, and it comes down to a specific fundamental property of quantum mechanics that has no equivalent anywhere in classical computing or classical communication. When you observe or measure a quantum system, you unavoidably disturb it. This isn't a limitation of current technology that better engineering might eventually overcome. It's a fundamental law of physics, confirmed across nearly a century of rigorous experimentation. This means that if an eavesdropper ever attempts to intercept a quantum encrypted message, tapping the entangled photons traveling through the fiber the same way a hacker might tap an ordinary internet cable, that very act of interception unavoidably disturbs the delicate quantum state being measured, immediately alerting both legitimate parties to the intrusion. Classical encryption, no matter how mathematically sophisticated, offers no equivalent guarantee. A sufficiently determined attacker can always, in principle, silently copy encrypted classical data, without either party ever knowing the interception occurred, and if that attacker later gains access to a sufficiently powerful computer capable of breaking the underlying mathematical encryption, all of that silently copied data becomes readable, potentially, years after the fact. Quantum communication doesn't just make eavesdropping harder, it makes it physically detectable at the moment it happens, a categorically different and, in many ways, strictly stronger security guarantee than anything classical cryptography has ever been able to offer. This is exactly the vulnerability driving so much of the current urgency around quantum computing more broadly, a threat security researchers call harvest now, decrypt later, where adversaries intercept and store encrypted classical data today, patiently waiting for a sufficiently powerful quantum computer to eventually make that stored data readable. A genuinely quantum-secured communication network sidesteps that entire threat model because there's no encrypted data being silently harvested in the first place. The security comes directly from the physics of the transmission itself, not from a mathematical puzzle that might eventually be solved by a sufficiently powerful future computer. This is precisely why the United States government has been treating quantum networking infrastructure as a genuine national security priority, not merely an interesting scientific curiosity. The Department of Energy directly supported the Northwestern and Fermilab demonstration, specifically because national laboratories handle exactly the kind of extraordinarily sensitive scientific and defense-related data that would benefit most from communication channels, physically immune to silent interception, regardless of how computationally powerful an adversary's future hardware eventually becomes. It's worth being genuinely clear, though, about exactly what these 2026 demonstrations do and don't yet represent, because there's a meaningful gap between proving entanglement can survive across a real city's fiber infrastructure and having anything resembling a fully functional, publicly usable quantum internet ready for ordinary people to actually use. And what researchers have proven so far is that the fundamental physical building blocks work reliably at metropolitan scale under real-world conditions using commercially available hardware rather than exotic, one-off laboratory equipment. What remains considerably further off is scaling this technology from city-sized networks spanning a few dozen kilometers up toward genuinely national or international scale, a challenge that requires solving a specific, extremely difficult engineering problem called quantum repeaters, specialized devices that can extend entanglement across much longer distances without the connection simply degrading and disappearing the way a classical signal does when amplified repeatedly. Unlike a classical repeater, which can simply copy and boost a degraded signal, quantum information cannot be copied at all. A fundamental restriction physicists call the no-cloning theorem, which means quantum repeaters have to work through considerably more sophisticated techniques, essentially performing entanglement, swapping in a carefully orchestrated chain across many intermediate nodes, exactly the kind of operation the New York demonstration specifically proved could work reliably at real metropolitan scale for the first time. Industry analysts and government roadmaps studying this exact trajectory have generally described quantum repeaters spanning several hundred kilometers becoming realistic within the next 5 years, forming genuine metropolitan scale networks connecting entire regions rather than isolated city test beds. with entanglement distribution stretching over 1,000 kilometers or more, remaining a goal for roughly the next 1 to 2 decades beyond that. The United States government has formally stated its own strategic ambitions in this exact space, laying out plans to enable functioning quantum networks broadly within the near term, with a considerably longer-term vision extending toward a genuinely comprehensive national quantum internet capable of leveraging networked quantum devices across the country over the following 2 decades. The European Union has pursued a broadly parallel strategy of its own, with an agreement between the European Commission and the European Space Agency working to build a secure pan-European quantum communication network specifically designed to connect government institutions, critical infrastructure, and other especially sensitive communication and data sites across the continent, treating this exact technology with the same kind of long horizon, strategically motivated urgency the United States has applied to its own domestic quantum networking efforts. It's worth stepping back here to consider why a story about photons traveling through fiber optic cable underneath New York City and Chicago deserves this much attention beyond the narrow world of quantum physics researchers who might normally follow this kind of news closely. The internet you use every single day, the one carrying your banking information, your private messages, your medical records, and increasingly the digital infrastructure underlying nearly every part of modern life, was built entirely on classical physics, on encryption schemes whose security rests on certain mathematical problems being too difficult for any existing computer to solve within a reasonable amount of time. That foundation has served remarkably well for decades, but it has always rested on an assumption that computing power capable of breaking that underlying math would remain forever out of reach, or at minimum, arrive slowly enough that defenses could be upgraded well ahead of any genuine threat. Quantum computing research, developing in parallel with the quantum networking breakthroughs described throughout this story, threatens exactly that foundational assumption, and quantum networking represents the other. Les Lemar discussed half of the same broader technological transition, not a way of breaking existing encryption, but an entirely different physics-based alternative to it, one that doesn't rely on mathematical difficulty at all, and therefore doesn't face the same long-term vulnerability to ever more powerful future computers. None of this means your ordinary, everyday internet connection is about to be replaced by some exotic quantum alternative anytime soon, and it's important to be genuinely clear about that, because the practical reality of where this technology currently stands looks nothing like an imminent, sweeping replacement of the internet as you know it. Accumulated infrastructure, standards, and enormous collective investment isn't going anywhere in the near term, and the vast majority of ordinary internet traffic, streaming video, casual browsing, everyday email, has no particular need for the specific, extraordinarily strong security guarantees quantum networking uniquely offers. What these 2026 demonstrations actually represent is considerably more specific and, in its own way, more consequential. They prove that the physical foundation for an entirely new category of communication infrastructure, one specifically suited to the most sensitive, highest stakes categories of data, government communications, financial infrastructure, critical national security systems, works reliably in the messy, noisy, real-world conditions of an actual American city, not merely inside the artificially clean confines of a university physics laboratory. That distinction between proving something works in theory and proving it survives contact with the real world is precisely the gap separating decades of interesting but ultimately impractical quantum physics. Research from something that finally starts looking like genuine deployable technology. Looking ahead, the most useful way to think about where this story goes next is to watch for exactly the kind of scaling milestones researchers themselves have already flagged as the natural next steps in this trajectory. Kumar's team at Northwestern has already stated their next target explicitly, attempting to perform full quantum teleportation and even more advanced quantum networking. Capability than the entanglement distribution already demonstrated, over a real metropolitan fiber network carrying genuine commercial traffic. Building directly on teleportation work, Kumar has already successfully performed inside a controlled laboratory setting. Watch, too, for whether these city-scale demonstrations begin connecting to each other, linking separate metropolitan quantum networks like the ones now operating in New York and Chicago into a broader, interconnected regional or eventually national system, the specific kind of multi-city expansion that would represent the next genuinely major milestone on the long road toward whatever a fully realized quantum internet eventually looks like. And watch for whether other countries, particularly those also investing heavily in their own quantum computing and quantum networking programs, begin publishing comparable real-world, metropolitan-scale demonstrations of their own, since a technology this strategically significant rarely remains the exclusive achievement of a single country for very long, once the fundamental engineering barriers have been shown to be solvable. It's also worth understanding a bit more about the broader ecosystem of quantum networking research happening in parallel across the United States, because New York and Chicago are far from the only places this exact kind of work has been quietly advancing, and seeing the fuller picture helps illustrate just how seriously this technology is now being pursued across the American research landscape. The Department of Energy has spent years building out a coordinated national quantum networking research effort spanning multiple national laboratories, including Fermilab's direct involvement in the Northwestern Chicago demonstration, part of a broader initiative specifically aimed at transforming how complex scientific problems get investigated and solved using quantum-enabled infrastructure. This isn't a single isolated research group working in obscurity. It's a coordinated multi-institution effort involving some of the most well-resourced country, treating quantum networking as important enough to warrant sustained long-term federal investment rather than a one-off. Curiosity Project. Universities and national laboratories across the country have been quietly building their own metropolitan-scale quantum testbeds over the past several years, each one contributing incremental engineering progress toward the same broad goal, proving that quantum communication can survive and function reliably in genuinely messy real-world conditions, rather than remaining confined to the artificially pristine environment of a specialized physics laboratory. There's also a meaningful commercial dimension to this story worth understanding, because Connect and Cisco's involvement in the New York demonstration wasn't purely academic curiosity, and looking at why a company like Cisco would invest resources into this specific technology reveals something important about where the broader networking industry believes this is all eventually headed. Cisco built its entire multi-decade business empire on classical networking infrastructure, the routers, switches, and software that quite literally run the modern internet as we currently know it. A company with that much accumulated expertise and that much at stake in the future shape of networking technology doesn't casually invest engineering resources into an unproven, speculative side project without genuinely believing there's a credible commercial future worth positioning for early. Cisco's specific contribution to the New York demonstration, the orchestration software functioning as what researchers described as a digital air traffic controller for the network, points directly at exactly the kind of expertise a classical networking giant is uniquely positioned to bring to this emerging field. The practical, unglamorous work of actually managing, coordinating, and scaling a distributed network reliably, exactly the kind of operational challenge Cisco has spent decades solving for ordinary classical internet infrastructure, now being adapted and applied to an entirely new category of underlying physics. It's also worth examining more closely what the practical, near-term applications of this technology might actually look like, because quantum networking's benefits extend meaningfully beyond the headline-grabbing security implications already discussed, into a category of application that gets far less mainstream attention despite potentially being even more immediately valuable. Distributed quantum computing represents one of the most promising near-term uses for exactly this kind of city-scale quantum network infrastructure, allowing multiple separate quantum computers, each with a limited number of qubits on their own, to be linked together over a quantum network and effectively function as a single, considerably more powerful combined system. Building one enormous, monolithic quantum computer with an extremely large number of qubits remains an extraordinarily difficult engineering challenge on its own, one that companies like IBM, Google, and IonQ have been racing to solve for years using various different physical approaches. Networking together multiple smaller, more manageable quantum computers, using exactly the kind of reliable entanglement distribution infrastructure just demonstrated in New York and Chicago, offers a potentially faster, more practical path toward achieving genuinely useful quantum computing power at scale, without needing to solve every single one of the hardest scaling challenges inside a single physical device all at once. This is precisely why the Connect and Cisco team specifically described their New York demonstration as providing a deployable blueprint for distributed quantum computing, not just secure metro-scale communication, treating the network itself as foundational infrastructure for an entire category of future quantum computing applications, well beyond simple point-to-point secure messaging. There's also a specific, almost poetic irony worth appreciating in exactly where this particular breakthrough happened. Because 60 Hudson Street, the commercial data center at the center of the New York demonstration, is itself one of the most historically significant telecommunications buildings in the entire world, a former Western Union headquarters that has served as a critical hub connecting undersea cables and telecommunications networks since long before the modern internet existed in any recognizable form. Routing the first genuinely commercial-grade, metropolitan-scale quantum entanglement demonstration directly through a building with that specific telecommunications history feels less like coincidence and more like a fitting symbolic marker, a physical location that has quietly anchored nearly a century of evolving communications. technology now hosting the earliest infrastructure for whatever comes after the classical internet as we currently understand it. There's also a meaningful global competitive dimension to this story worth understanding, because the United States is far from operating in isolation when it comes to quantum networking research, and other major world powers have been pursuing comparable ambitions of their own with genuine seriousness. China has invested enormous state resources into its own quantum communication infrastructure for years, most famously demonstrated through its MIXUS satellite, launched back in 2016, which successfully distributed entangled photons between ground stations separated by more than 1,000 kilometers, an achievement that predates, and in terms of sheer distance, actually exceeds what the recent American metropolitan fiber demonstrations have accomplished so far. China has also built out an extensive fiber-based quantum communication backbone connecting major cities, representing years of sustained state investment specifically in this exact category of infrastructure. What distinguishes the recent American demonstrations in New York and Chicago isn't necessarily raw distance, since China's satellite-based approach has already proven entanglement can survive over considerably longer ranges under the right conditions. It's the specific combination of commercially available hardware, deployment directly through existing telecom infrastructure, already carrying ordinary internet traffic, and genuine multi-day sustained reliability, precisely the practical, deployable characteristics that distinguish infrastructure ready for eventual real-world commercial and government use from an impressive but narrowly scoped scientific demonstration. Both countries, alongside the European Union's own parallel efforts, are effectively racing toward the same underlying goal from different technical angles, treating quantum networking as a genuinely strategic technological priority rather than a purely academic pursuit. It's worth being honest, too, about the specific technical hurdles still standing between where this technology currently sits and a genuinely mature, widely deployed quantum internet, because understanding those remaining challenges realistically helps calibrate sensible expectations for how this story is likely to unfold over the years directly ahead, rather than either overselling the pace of progress or dismissing it entirely. Beyond the quantum repeater challenge already discussed, researchers still need to solve considerable engineering problems around quantum memory, the ability to reliably store an entangled quantum state for a meaningful period of time without it decaying, a capability essential for synchronizing entanglement, swapping operations across a network where different photons inevitably arrive at slightly different times depending on the specific path and distance each one travels. Cost remains a genuine practical barrier as well, since the specialized hardware required to generate, detect, and precisely measure individual entangled photons remains considerably more expensive and technically demanding than the mass-produced equipment underlying ordinary classical internet infrastructure, a gap that will likely need to narrow substantially before quantum economically viable for anything beyond the highest value, most security-critical applications, currently justifying the expense. None of these remaining challenges diminish the genuine significance of what was actually proven in New York and Chicago throughout 2026, and it's worth being clear about exactly why these specific milestones matter so much within the broader arc of this technology's development, rather than treating them as merely one more incremental headline in a field that has produced plenty of impressive-sounding but ultimately narrow announcements over the years. Every genuinely transformative technology in history has passed through a similar sequence, moving from theoretical possibility to isolated laboratory proof of concept to messy but functional real-world demonstration, and only then, gradually, toward genuine widespread practical deployment. The internet itself followed almost exactly the same trajectory, spending decades as an obscure academic and military research project long before it became the ubiquitous, everyday infrastructure billions of people now depend on without a second thought, a slow, unglamorous evolution that looked nothing like an overnight technological revolution while it was actually happening. Quantum networking, based on what researchers in New York and Chicago demonstrated across 2026, has now definitively crossed the specific threshold separating isolated laboratory proof of concept from genuine, functional, real-world demonstration, operating not inside a pristine, artificially controlled physics laboratory, but underneath the actual streets of two of America's largest, busiest, most demanding metropolitan environments, sharing fiber optic infrastructure directly with the ordinary, chaotic internet traffic millions of people generate every single day without ever knowing anything unusual was happening beneath their feet. The underlying achievement sitting at the center of this story deserves to be taken seriously on its own terms, independent of exactly how quickly it eventually scales toward broader, more practical deployment. For the first time, using commercially available hardware rather than exotic laboratory-only equipment, American researchers proved that quantum entanglement, one of the strangest, most fundamentally non-classical phenomena in all of physics, survives being pushed through the actual already existing fiber optic infrastructure of a real, working American city alongside real commercial internet traffic, reliably enough to sustain extended operation. Over multiple days at a time, the classical internet, built entirely on mathematics rather than physics for its underlying security, genuinely has no equivalent answer to what this specific capability offers, because the security quantum entanglement provides doesn't depend on any assumption about what future computers will or won't eventually be capable of calculating. It depends instead on a law of physics that has survived nearly a century of the most rigorous experimental scrutiny science has ever applied to any single idea. And that is precisely why this quiet demonstration, running through fiber optic cable, most New Yorkers walked directly over without ever knowing it was there, may end up mattering considerably more, over the long run, than almost anything else happening in technology news this year. If you want to keep following exactly how this quantum networking story develops, including whether these city-scale demonstrations successfully expand into the kind of broader interconnected national network researchers are already working toward, make sure you're subscribed, because this is genuinely one of the most consequential, least publicly understood technology stories currently unfolding anywhere in the world. Thanks for watching all the way through, and don't forget to like and subscribe so you catch the next update in this story the moment it happens.